Hello and welcome to 24 Hours Have Passed, SQL Server 2014 edition. We are excited that you could join us today for Jos de Bruyn's session on SQL Server 2014 In-Memory OLTP Performance Troubleshooting. This 24 Hours Have Passed event consists of 24 consecutive live webcasts. The recordings from all of the sessions will be available next week at www.24hoursofpass.com. My name is Vicki Van Dam, and I am a project manager for Pass HQ, and I am your moderator for this evening's sessions. I have a few quick introductory slides before I hand the reins over to Jos, and he'll be speaking for about 40 to 45 minutes, and then we'll move over to Q&A. If you're having any issues throughout the session, just raise your hand using the hand icon on the right-hand side of your screen. To maximize your screen, you can use the Zoom button located on the top of the presenter window. Feel free to enter your questions into the Q&A field at any time. That question pane is located on the right side of your screen. We'll get to the Q&A portion of the session at the end after Jos has presented his content. At that time, I'll read your questions out loud, and since you're all muted, you'll need to submit those questions through that Q&A field. There's also going to be a short evaluation that will appear at the end of the session. Your feedback's really important to us and to our presenters, so please take a moment to complete the survey. I'd like to take a moment to thank our event partner, Microsoft, who's one of our global sponsors. The staging of 24 Hours Have Passed would not be possible without their support, and they are the reason that we are able to provide this event for free to the Pass community. Next, I'd like to bring your attention to the upcoming Pass Summit. This will be taking place in Seattle, Washington from November 4th to 7th. The Pass Summit will feature over 190 sessions with world-class SQL Server experts. This conference is planned and presented by the SQL Server community for the SQL Server community. Pass Summit is the largest gathering of SQL Server and BI professionals in the world. With over 5,000 attendees, Pass Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. Most importantly, Pass Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and the skills you need to stay ahead of the curve. You can contact your local chapter or reach out to one of our virtual chapters for one of their discount codes to save up to $150 off. Get the most out of your dollars and optimize your saving by registering before Friday, June 27th. You can find out more by visiting www.passsummit.com. And now, allow me to present Jos de Bruyn. Jos is a Senior Program Manager on the SQL Server Database Systems team. He has worked on the Hackathon project, bringing the in-memory OLTP database technology to SQL Server. Jos was formerly an assistant professor, has a PhD in knowledge representation and semantic web technology. Wow, that sounds impressive. So without further ado, I give you Jos de Bruyn.
Thanks, Vicki, for the nice introduction. So the feature we're talking about in this session, and which is also featured in a number of other sessions in this 24 Hours of Pass, is In-Memory OLTP. So this is an exciting new feature we introduced with SQL Server 2014 to optimize the performance of OLTP workloads. It does so by using in-memory technology. We optimize data structures, algorithms, and access patterns specifically for your data residing in memory, and we have also other optimizations, like we remove scaling bottlenecks, including locks and latches, and we use native compilation to improve query execution. So if you look in total at all the sessions that you see at this 24 Hours of Pass, there we had some introductory sessions and also some sessions which looked at in-memory OLTP from the developer perspective, from the DBA perspective, and also George was talking a little bit about what is the methodology for migrating an existing application to the new in-memory OLTP technology. So how can you best leverage in-memory OLTP in your existing applications? Now, what I want to look at in this session is, well, you have started this migration process. You have migrated maybe some tables and some stored procedures over to in-memory OLTP, but you are having some issues with performance. The performance may not be exactly what you expect. There can be several things going on here. Like one aspect that I mentioned, one benefit of in-memory OLTP is great scaling, for example. So if you have a lot of concurrent transactions in your system, a lot of cores in your system actively working, you can get great scale. If you have, for example, just one thread working, just one query executing, you might not get the same type of benefit. Another important aspect is the indexes. So we have two types of indexes for memory optimized tables, and you need to be very careful in which index to select. And in this session, I want to show you a little bit based on demos, like how you can troubleshoot this, how you can figure out whether you have the right types of indexes and how to remedy these situations. So main things I want to focus on is, first we'll talk a little bit about troubleshooting tools. I will kind of gloss over them. Then we'll talk a little bit about hardware and concurrency. So you need to always make sure you have the right hardware for testing. Make sure you test for the right level of concurrency. Then we'll look at troubleshooting, issues around indexes. And if we then still have some time left, we'll look specifically at troubleshooting query plan issues with natively compiled stored procedures. The key ones here, I think, are the hardware concurrency topic and the index troubleshooting. You can, if I don't manage to get to the native proc topic in this session, you can download the slides and use those as a reference. And also the demo scripts I will show you, they will be made available through the website. So let's look at the first topic. So when you are migrating your application to in-memory OLTP, or in general, if you're developing an application that leverages in-memory OLTP, there are a number of considerations, a number of things you want to keep in mind. So first, I'm listing here a couple of characteristics of applications where you can expect performance improvement by leveraging in-memory OLTP. And the more of these aspects are used by your application, in general, the more performance improvement you can expect. So first, write-heavy apps. In-memory OLTP, we see that the writes are generally very efficient compared with traditional disk-based database systems. So particular inserts, updates, deletes, they're very efficient. Then OLTP-style operations, where you're dealing with generally a limited number of rows that you are processing. You have short-running transactions. Those are a good fit. And in terms of the specific lower level operations that you're doing, if you're doing more point lookups, that fits better with in-memory OLTP. If you do a lot of large index scans, you're scanning a lot of data, retrieving a lot of data, not such a good fit. Nested loops joins, that's similar. So nested loops join is you would typically use that in kind of a foreign key pattern, like if you have, for example, a sales order header table, sales order detail table, and you want to get all the data for a particular sales order ID, you look up the sales order ID in sales order header table, you do a nested loops join with a sales order detail, get the details for the sales order. That type of pattern works very well with in-memory OLTP. Then high levels of concurrency. So we remove a lot of, we actually remove all latching and locking. We don't have any latches or any locks with in-memory OLTP. So we remove all the blocking. That means that you can get great scaling. So the higher the degree of concurrency, the more concurrent transactions you have active in the system, the more performance gain you will get from in-memory OLTP. And finally, using natively compiled stored procedures. So we have these new natively compiled stored procedures which compile T-SQL statements, T-SQL queries to native code, to a DLL for very efficient query execution. So if you use those, you will get more performance gain, and especially the more logic you manage to put inside that procedure, the more gain you will get. Well, there's a trade-off here because we don't support all T-SQL constructs in there. We don't support all query operators inside natively compiled stored procedures. So the question is, not all your logic might fit in there, but the more you can get to fit inside the native procs, the more performance improvement you can expect to get from using those. Then in terms of the hardware, what we have seen is that there are kind of two key aspects that you do need to keep in mind. And I would say these are usually kind of obvious for production systems, but maybe not so much for test systems, especially if you want to run some simple tests on your desktop machine or your laptop. You might not think about these aspects. So the first is the log IO subsystem. So every transaction, also in memory OLTP, with every transaction, when you commit, we write a record to the log, and this is hardened to disk in order to guarantee durability. Right? After a transaction commits, you want to be sure the data is durable, and if you restart the server, the data is there. Right? So we need to do the log IO at the end of every transaction. So if you have a slow disk, let's say a spindle, for example, then the log IO becomes a bottleneck, and if you are in your transactions you're just spending a whole lot of time on writing to the log, you will not get a whole lot of performance gain overall. Even though the logging we do with in-memory OLTP is more efficient than with disk-based tables, still the latency is an issue. So if you have slow log, you will not see performance gain. Also no degradation, but no performance gain. So you need to make sure you can keep up. But we've seen usually if you use SSD or flash storage, you will be able to keep up. You will be able to see significant performance gains. And the second one is about the degree of concurrency. So of course you need to drive your workload with enough connections, with enough concurrent transactions in order to stress the database and to get the throughput you want. But also from a hardware point of view, you will need to have enough cores available to actually perform that work. You cannot have more concurrency in the system than that you have cores. Right? If you have, for example, a 4-core system, you cannot have more than 4 concurrent transactions running at any time. So if you are testing on a simple desktop machine with only 4 cores, you may not see as much performance gain as when you have a mid-range server with, let's say, 2 sockets, 12 cores each, 24 cores in total, throw on hyper-threading, you have 48 cores. You will see a lot more performance gain due to the scaling that we get with in-memory OLTP. And also then testing, so you need to have the right hardware. So we usually recommend to use hardware that is close to whatever you have in your production system. And also with respect to the testing, if you want to test whether in-memory OLTP really benefits your application, you will want to test at production scale. Make sure you have the same level of concurrency as you're also seeing in production to validate that it works, right? If you just run a single query, that will often not produce a lot of gain, right? You want to really test at scale, stress the system similar way as you do in production, have the same read-write ratio, have the same number of connections, etc. Troubleshooting tools. I don't want to go into too much detail. when I myself do troubleshooting, and I'm definitely not a SQL Server troubleshooting expert, I typically use these kinds of tools. I do want to highlight two things. Perfmon, so we have a number of new perfmon counters. I think I have one example on the next slide. For testing, I often use OStress. So OStress is a tool shipped by CSS, which can actually simulate a stress workload, which can be very useful for really stressing the system and seeing what kind of performance gain you can get out of it. And also with In-Memory OLTP, we have a number of new DMVs that you can use for troubleshooting. Instead of internal perfmon counters, what I just want to highlight here is we have a number of new XTP counters. Those are the new In-Memory OLTP counters. What I'm highlighting here is XTP transactions. So one thing to keep in mind is that if you have transactions run by the new natively compiled stored procedure, they are not counted by the old perfmon count for databases transactions per second. They are only counted by the XTP transactions created per second. So that is something to keep in mind if you're using perfmon for profiling your throughput. So with that, I want to go to the first demo. What I want to do here is show show a kind of typical scenario where you go from disk-based tables to memory-optimized tables, and I will gradually go and show that, well, if I test really at greater scale, I will see more performance improvement. So the database I'm using here is AdventureWorks with a particular extension for In-Memory OLTP, and there is in the deck, in the resources towards the end of the deck, there is a link to the download of this extension, so you can install it yourself and play around with it. So first, let me go ahead, use my database. So the workload I have here is a sales order processing workload. What I'm going to do is just insert sales orders, and I have a particular stored procedure for that. So in this case, this is my traditional stored procedure working with the traditional disk-based tables. And what the stored procedure does, it takes a number of arguments for the sales order header, and it takes a TVP, table value parameter, for the sales order details for the individual line items. And then based on that, it will calculate a subtotal for the sales order. It will insert a row into the sales order header table, including the subtotal, and will also insert the details into the sales order detail table based on a join of the TVP with a number of other tables to get the details around special offers and product pricing, etc. So let me go ahead and I will create this procedure. And the workload I'm going to run here, just for benchmarking purposes, it's a simple workload. Just on this single thread, I'm going to put together a sample sales order. It will have a total of 5 line items. So the sales order will have 1 row for the header, 5 rows for the line items, and I'm going to insert this same sales order 20,000 times. And these will be 20,000 invocations of the insert sales order stored procedure, so 20,000 transactions. And I'm going to check how long this actually takes. So let me go ahead and run this workload. So I'm now going to insert 20,000 sales orders. One thing to remark here is that I am doing this on a single thread with a single connection, right? So this is certainly not testing at production scale, because in production you will of course have many concurrent sessions that will concurrently insert the sales orders. And what I am seeing here is that my elapsed time for my 20,000 orders was about 8.8 seconds with disk-based tables. So the first step I did out here was I migrated my tables to memory optimized. So I'm not showing the actual tables here. I just want to show you the workload I'm doing. The tables will have exactly the same schema, and if you look at the sample, if you download it, look at the sample, you can look at these tables, and you will see what they look like exactly. So what I have in this case is a traditional sort procedure that just does the insert of the sales orders into a memory optimized table, but otherwise the definition of the procedure is exactly the same. So we have the same parameters and the same T-SQL in the content. So again, we have calculation of the subtotal, insert of the row in the sales order header table, and then the insert of the details into the sales order details table. So let me go ahead and create this stored procedure. And then again, I'm going to run exactly the same workload, but instead of the disk-based table, I will insert into the memory optimized table. And one thing to keep also in mind here is I'm using a traditional interpreted T-SQL table here, so I'm not yet using a new memory optimized table. And what we could see is, well, we do see some performance gain already, so from 8.8 to 7.7 seconds, but actually in these workloads, in this particular workload, when you're just running single-threaded with elapsed time, there's always some variation. Probably has to do with other processes running on the same box. But some performance gain, right? But we can probably do better. So the next step what I'm doing here is, instead of this interpreted T-SQL procedure, I'm using a natively compiled sort procedure. So the parameters are pretty much the same, except that you will see here that I'm actually using some not null constraints. These are supported for natively compiled sort procedures, not yet for traditional T-SQL. But having these not null constraints for your parameters just helps you avoid some null checks, which are additional CPU instructions you may want to bypass. Apart from that, I mean, this is just boilerplate natively compiled stored procedure header, and the content, but the content of it is exactly the same T-SQL script as you saw before. So let me go ahead and create this procedure. All right. And I'm going to, again, execute the exact same workload. So I'm going to insert, again, 20,000 sales orders. By the way, I'm running all these tests on my humble laptop. So if you have a decent server, you might see somewhat different results. But what we're seeing in this case is that, in fact, we get already a bit more performance gain, right? We went from, what was it, 8.8 seconds with disk-based tables to 7.7 when accessing memory optimized tables through interpreted T-SQL, and we went down to 5 seconds when going to native. So that is all in all almost 2x performance gain, right? 8.8 to 4.9, okay, not exactly 2x, but close, right? So that's already pretty good. But it's also pretty far from the 30x that Microsoft promised you. Okay, we did not actually promise you 30x for all workloads, but we were just saying up to 30x performance improvement, right? It always depends on the workload. But again, in this case, the performance gain is somewhat limited, especially because I'm doing this everything in the same session, in the same connection, so I have no concurrency in the system. And I actually only have 4 virtual cores in my laptop, so I cannot get a whole lot of concurrency in the system here, but I should be able to get a little bit of concurrency in here. So for the final test, what I want to do here is actually spin up 20 connections and start inserting orders in there. So what I'm going to do is I'm going to open 20 connections and insert a total of 40,000 orders using these 20 connections. So and I'm going to use this O-stress tool. This is a command line tool shipped by CSS, which essentially what it does is it spins up a number of connections. In this case, 20 connections, and you can say each connection should execute this particular T-SQL command X number of times. In this case, I'm saying execute it for 100 times. And I have a script here which is very similar to a previous script, except that the script inserts the same sales order 20 times instead of 20,000. But therefore, we have these iterations. Okay, so let's go ahead and run this. So I'm going to run this on the command line. It is now getting started. So we have now O-stress has opened these 20 connections and is now inserting the sales orders into my database. And this is again the disk-based tables. So by now I have started to stress the system. Right? There are many more connections than I have actual cores. So I should be able to use my cores. Now let's have a look at what is the result. So what O-stress tells you how long it took for all these threads to finish all their work. So in this case, it took about 16 seconds to insert all these 40,000 sales orders using the 20 threads, using the 20 connections. And this is my baseline for disk-based tables. Now let's do the same for memory optimized tables. Again, same logic, except instead of disk-based, it's memory optimized. So again, 20 connections, inserting a total of 40,000 sales orders. And what we can see in this case, we take 3 seconds instead of 16, which is a 5.5 times performance improvement, which is a lot more than I saw before, which was less than 2 times. Right? And this comes from the concurrency benefits you get with In-Memory OLTP, because we don't have any locking and latching, so we scale much better. So the more cores you throw at your problem, and the more connection you throw at it, the more scaling and the more performance benefit you will see. And this is still not too impressive compared with maybe some other demos you have seen. But that is because this is on my lowly laptop with only the 4 virtual cores. If I run this on a machine which has 16 virtual cores, a 2-socket box with like older generation, I get about 20x. And if I run this on a modern machine, Ivy Bridge 2-socket, 12 cores, on each socket, 48 logical cores total, I get about 50x performance gain in this particular workload. So again, it depends on the hardware, the level of concurrency your hardware can sustain, and the level of concurrency you use in your testing, what type of gain you get with this style of workload. Okay, let me also make sure I clean up so that my next demo will run smoothly. Okay, so that was the first one. So let's move on. The other main topic I really want to get to is indexes. So we have these 2 types of indexes for memory optimized tables. One type of index that we have is the non-clustered index. And this is somewhat similar to the non-clustered index you have for disk-based tables. It is, in terms of capabilities, you can do similar types of operations. So usually we recommend, if you're migrating your table, use that as the baseline. But we also have the hash index. And that is our more performant index. It is specifically made for point lookups, and with point lookups and inserts in particular, you can get much better performance than with non-clustered indexes. But there are some operations they don't support. When thinking about the index issues, so with hash indexes, not only operations they don't support, but also when you define a hash index, you need to specify the bucket count. So you need to specify the size of the index. And the size of the index will actually not change. And the bucket count, you need to size it based on the maximum number of rows you are going to expect in the table. And if the bucket count is too low, you can suffer from performance issues. And also, hash indexes don't perform well if you have a large number of duplicates. So you could get some performance issues there. So for bucket count, you want to have it at least as many buckets as you have number of rows. I mean, okay, if it is a bit less than the number of rows, it's okay. But if it's like 5 times less than the number of rows, you're starting to run into problems with performance. Then in terms of index selection, choosing whether to use a hash index or a non-clustered index. So with hash index, 2 particular operations that are not supported, which catches some people by surprise when migrating their applications, is first, you don't support search on a subset of the index key. So you cannot search on leading index key columns if you have a multi-column index key. And this is supported with traditional cluster and non-cluster indexes. So it can get you by surprise. So if you don't specify all the columns in the hash index key in your where clause, we cannot use that index for searching. So we need to revert to a full index scan, which can obviously degrade your performance. Second thing is, if you have any operations that require a sort order, like inequality seeking, searching for a range of values, like date range, for example. You want to search everything for all values for a particular week, for example, or you want to have everything returned in sort order. That's all not supported by hash indexes, because in a hash index everything is hashed, so the order of the index keys is not preserved when hash index is created. So these are things you want to keep in mind. So if you need any of these operations, use a non-clustered index. On the flip side, point lookups are much more efficient with a hash index, and also inserts into a hash index are much more efficient than with non-clustered index. And also one thing you want to keep in mind, I'm not showing this here, but you may run into this issue, is that during database recovery, when we start up the database, when we start up the server, and we bring the database online, we read in all the data for the memory optimized tables. And the way we read this data is we insert it into the table. And if an insert in a non-clustered index are less efficient than in a hash index. So we have seen cases where if you have very fast I/O, the non-clustered index can sometimes become a bottleneck during recovery. Okay, so let's get to the troubleshooting. So I want to address these 2 points that weren't on the slide. So first I want to look at bucket count, and then look at index selection. And when you migrate your table, what are potential consequences of picking the wrong index, and how do you diagnose these issues? So first, the bucket count. So what I'm going to do here is, let's see, want to make sure everything is clean. So I'm going to create a table here which has a number of hash indexes. So I have here a simple table, sales order header test, which is a simplified version of a sales order. I have here my sales order ID, order sequence, is an integer, I have an order date, as well as a status. So the indexes I have my sales order ID, the hash index, with a bucket count of 260K. So this is probably the number of rows I expect. Order sequence, I have an index on order sequence with a bucket count of 20,000. So maybe I'm expecting 20,000 values here and whatnot. So for status, this is like a tiny int, so probably not many values. So maybe a bucket count of 8 might suffice. And then I have a non-clustered index, of course, an order date, because on dates you will typically want to do inequality searches, or you want to get your data in order of the date. So, okay. So I created my table, and what I'm going to do now is perform an insert operation. So this particular insert inserts 262,000 rows into this table, but we have what do these rows look like? Well, the sales order ID is the identity column. This means I will get integers in ascending order in that, so each row will get a new integer. And what the other values I have is, well, I'm inserting also an integer, a unique integer for in order sequence. So also each row will get a different value for the sequence. And I use the current date time for the date field, and I use like 8 different values for the status. So we have in total 8 different status values. Now this whole insert operation is taking disturbingly long. As you can see, it is already running for more than a minute, and I expect In-Memory OLTP should be fast, right? I can expect about 1 million rows to take a couple of seconds at most, usually. So this is taking unusually long. It should finish any minute now, though. So what I then want to do is when the inserts finish now, so they finish now. Let's see how long they took. It took 1.5 minutes. I'm not happy about that. So I suspect it might be an issue with the hash index bucket count. So as a first order of troubleshooting, what I'm going to do is just look at the bucket counts and look at the unique number of unique index key values. Because our first order of recommendation is always bucket count should be at least the number of unique index key values. So let's look at those. So for my primary key index, I have the exact name, exact number of values as I have buckets. So that looks fine. For order sequence, I have 32K buckets, but 260K values. So that's definitely too low. And when I look at status, that seems okay. So I have 8 status values, 8 status buckets. That might be okay. I don't know. But this does not really get me to the core. I mean, the order sequence might be bad, but I don't know yet what the hash index actually looks like or how bad it is. So for that, we actually have a new DMV, which is DMDB XTP hash index stats. And we recommend using this particular query to look at this DMV and to analyze the health of the hash indexes. So two particular columns I want to draw your attention to. That is the empty bucket percent and the average chain length. So empty bucket percent, you will want to have at least 30% of your buckets empty. If it is lower, it means that there is a lot of pressure on a lot of the buckets and a lot of values will get mapped to the same bucket, and that is bad. You will have a lot of collisions. There will always be some empty buckets. That is just due to the nature of the distribution of the hash function. You have a Poisson distribution, which is pretty much a random distribution, so there will always be some empty buckets. And to get a healthy distribution, you will want to have at least 30% empty. So if we look at the status index, 50% empty, looks good. Order sequence, we already saw there was some trouble, and indeed we see 0% empty, in total only 13 buckets empty, so definitely that is not good. Definitely bucket count too low there. If you look at the primary key index, it's over 30%, 36%, so that's healthy. But now let's look at the average chain length. So what this represents is the number of rows that are actually in a bucket. So what the data structure looks like is you have these buckets in the hash index, and you have a number of rows, and these rows are all in a chain, essentially a linked list. And the longer this chain, the harder it is to find a particular row in this chain, the more work you need to do, because you might need to walk this entire chain just to find one row that is there. So that's a lot of work. And even for inserts, right, you need to walk a lot of this chain to find the right place to insert your row. So this is very unhealthy. So in fact, this high bucket percent with combined with high chain length is an indication there's a lot of duplicates. And for a lot of duplicates, we recommend using a non-clustered index instead, because they perform better if there are a lot of duplicates. If we look at order sequence, average chain length 8, well, 8 is not the end of the world, but certainly suboptimal. If we look at a primary key index, average chain length of 1, that is optimal. So that is great. So what we'll need to do here is fix the status index. We'll need to make it a non-clustered index to deal with the duplicates, and we'll need to bump the bucket count of order sequence. So what I'm going to do is drop the table and recreate. Of course, in production, you would first copy out your data, maybe through BCP or into a heap before you drop the table. And what I'm going to do here is, because I'm doing maintenance anyway, I'm going to bump the bucket count from a primary key index also to 1 million to account for possible future growth. Bump the bucket count sequence to 1 million and change the status index to be non-clustered. And I will leave the order date index alone, because it was a non-clustered index and we did not have any problems there. Now I can verify what are my actual bucket counts, and as you can see, I have here 2 hash indexes on my table, the order sequence index and the primary key index, both 1 million buckets. As you can see, it's a bit more than 1 million because we always round up to the next power of 2. So let me again insert this 260,000 rows, and let's see how fast this is now. And we can see this is indeed a little bit faster. We can see this now, instead of 1.5 minutes, this took now 3 seconds. As you can see, there's an order of magnitude difference because we needed to do a lot less work during the inserts. So this is something we have seen actually with a lot of customers who had bucket counts that were too low, and tables would take forever to load. We've seen cases where, like, a table with 10 million rows took 5 hours to load just because a bucket count was set at 150 instead of 10 million. There you go. So be very careful with the bucket counts. And let me now check the health of the hash index just to make sure everything is good. So both hash indexes have an empty bucket percent of 77, which is perfectly fine. That's perfectly healthy. If this is high, that's usually not an indication of a problem. Average chain length of 1, that's perfect. So my hash indexes are in tip-top shape. So then the next point I want to get to is the index selection. So I want to make sure that I pick the right type of index when I'm considering non-clustered versus hash. So what I'm going to do here is I'm going to consider actually a sales order detail table, example sales order detail table, which has a hash index on product ID, and it has a hash index for the primary key on sales order ID, sales order detail ID. Right? And the way I may have obtained this table is by migrating an existing disk space table and converting the existing clustered, non-clustered indexes to new hash indexes. So what I'm going to do is populate it with the sample data from AdventureWorks, just so we can play around with it. And it is a fairly small data set, so 120,000 rows. You will see bigger performance issues actually if you have more rows. But already performance problems based on index selection will become pretty evident from this test. So what I'm going to do now is run a very simple workload. So first I'm going to take my disk-based table, which had clustered and non-clustered indexes on product ID and sales order ID, sales order header ID, and I'm going to do a simple lookup on sales order ID from my sales order detail table, and then I'm going to do a lookup on sales order ID in sales order header and join it with my sales order ID table. I'm going to do this 1,000 times, see how long this takes. Took 21 milliseconds for my disk-based table. Now for my memory optimized table, I'm going to do the same thing here. I'm going to run this. Now this is certainly not 21 milliseconds. It keeps running and running and running. Now, certainly when it starts to behave like this, you know there's something wrong, and usually whenever something is slow, indexes are at fault. So let's stop this workload and start troubleshooting this. So the first thing I want to look at are query execution statistics. So I want to see here which queries are taking the most time. So I'm looking at the total worker time, which is the total CPU time spent by these queries. So I have here 2 queries that were each executed 1,000 times. Those are probably the queries on disk space tables, and took in total 5,000, 10,000 microseconds. And now looking at these 2 here, they're not even executed 1,000 times, but they did an order of magnitude more work. If I look at what are these queries, if I copy paste them from DMV results, we can indeed see these are the 2 queries I was running before. Another way you can look at this is through a particular in-memory OLTP DMV, which is DMDB XTP index stats. So you can look at index utilization. And 2 particular things I want to call out here: scans started, which is the number of times the in-memory OLTP engine started to access the index. And the scan started does not mean it does an index scan. This could be an insert or a seek or a scan or whatnot. Right? So scans started and rows returned. So if you have a low number of scans started and a high number of rows returned, it means you're not doing a large number of full index scans, or you're scanning at least very large parts of the index. And if you're expecting to do more point lookups, then these numbers should be similar, or scan started even higher than rows returned. In this case, scan started here is much higher than rows returned because these were the inserts that were performed in the table. So now I saw that these queries were the culprits. I saw that this is probably a problem with indexes. So now let's look at the query plan for these particular queries. So let me go ahead and look at the query execution plan. And let's zoom in on the ones of interest here. So we have here these 2 queries. Let me zoom in a little bit here. So this is the first select, where in fact we are doing an index scan followed by a filter operation. So we could not do the seek, in this case a seek on sales order ID. And for the second one, we are in fact doing a seek on sales order header, but we're doing again a full table scan on sales order detail followed by a filter, which means we are not doing the right seeks. And let's look in detail at what the filters are looking for. The filters are in fact looking for sales order ID. So I want to seek on sales order ID, but I cannot seek on sales order ID. So why is this the case? Let me see if I have here the query for the index. Yes, let me verify the indexes that I actually have on the table. And what we have, the primary key index, is a hash index on sales order ID and sales order detail ID. So it has a composite key, and I'm just looking for sales order ID, but because it's a hash index, I cannot seek on just a subset of the key. So I always need to provide both values, both sales order ID and sales order detail ID. Then the next, I think, I think I will skip over the next part, which is about order requirements. If you run this yourself, you will see that the queries, because we have a hash index on product ID, we cannot run order by queries, and we cannot run inequality seeks using that index. So we'll need these additional operators, so therefore they will run slower. So what we need to do to fix this is, in this case, we need to seek on sales order ID. So we add an index, a hash index in this case on sales order ID, so we can seek on that, and we change the hash index on product ID to be a non-clustered index, such that we can do ordered scans. And let me create that table and insert the sample data. So when we do now the point lookup operations, we see this is now also in milliseconds instead of waiting many seconds. It's now also in milliseconds, and we will also see that when you run the queries that have these ordering requirements, they will also run really fast, like 0 milliseconds and 0 milliseconds. So it is really key when you migrate your tables to In-Memory OLTP to really think about your indexes and use your non-clustered index as a safe baseline, and then think about optimizing by using hash indexes for cases where you need to do point lookups, and always make sure that you have all the columns of the index key in the where clause, so you can search on it. So, as suspected, I don't have enough time to go through the planned troubleshooting. I do recommend you to take a look at troubleshooting tools. They are mostly the same as for traditional T-SQL, but there are some things you do need to keep in mind. There are some references here, also references in the deck. On this slide, we have some references to the documentation around the various topics, and I would recommend you to take a look at those, and also to download the sample. At the top you will find a lot of documentation of the sample and also links to downloading the sample, and I would recommend to download it, play with it, download the scripts for this session, and run the queries and do the questions. Do the troubleshooting yourself. So with that, I think we are at the Q&A.
Thanks, Jas. That was great. You know what? You've obviously designed an excellent presentation, because we actually don't have any questions. Oh, we just got our first one here.
Okay.
Okay, so let me read this aloud. So the SQL Server operating system allows one active thread per scheduler. What is the case of In-Memory OLTP SQL 2014, and why SQL Server creates only one scheduler per logical CPU? Why can't we think of active multi-thread per schedule and gain performance?
Well, In-Memory OLTP leverages SQL OS, both for memory allocation as well as for things like scheduling. So, and we did not change any of the logic of the schedulers. So all the work being done with In-Memory OLTP is being scheduled by the SQL OS schedulers. And yeah, why do we have one per CPU? I mean, I'm not sure. I did not do the design myself. I guess, well, the CPU can only do so much. You only have one CPU can only run one instruction at a time, right? So therefore, it makes sense to schedule only one thread at a time. Potentially, there are optimizations. I don't know. I'm not really a SQL OS guy, so I'm afraid I cannot give a comprehensive answer on that.
Okay, we do have another question. Actually, Diana's wondering if the scripts from your session are available, or if you'd be willing to provide them.
Yes, these scripts will be made available on the 24 Hours of PASS website. Yes.
Great. Well, I think that wraps up our questions, Yas. Thank you for delivering an excellent session, and yeah, we'll get those scripts up onto the website as well as your PowerPoint, and the recordings, just for everyone's knowledge, will be available in a week. Thanks again, Yas, for a great session, and thanks everyone for attending.
Yeah. Thanks.